All right, so finish writing what you're writing, and then let's go ahead and check the part 3, since most of us have our laptops up, and we can kind of do that together. And then we'll go back through the textbook. If it's not before the lab, it'll be after the lab, because it was a bit easier than part 3. So let's roll part 3, and we're going to check each part and talk about each part. So if you have it pulled up on your laptop, you might annotate or make a couple of notes if you get it wrong. Okay? So part 3, number 1, what'd you guys get? Say it out loud. I hear B's and D's. Okay, hand raise. B. B. Nobody. Okay, A. C. All right, let's try this again. You have to participate in my survey. A. B. C. D. All right, so about 4 of us got it right. The answer is D, because at the part on the graph where it says time 4, it told you initially, and I'm going to write it on the board so my viewers at home can't see this, so maybe take a couple notes for them if you can. You had the reaction A plus oxygen equilibrates to A dash, or A bonded to O. What did you have initially for A? Millimoles wise? 0.10 millimoles, okay, or millimolar. What did you have for oxygen initially? 0.2 millimolar. At the end, once equilibrium was achieved, how much do you have of the AO? It told you at time 4 seconds, if you look at AO, it's approximately what? It's approximately 0.4. I know it's a little above, but it did say approximate, so you will be fine with estimation. So at the final, or at the time 4, you made it to 0.04 millimole. Well, how do these react? In what ratio? 1 to 1 to 1, right? So if you have 0 of this, you added 0.04. So how much did you react with each of these? You reacted, so the same amount, 0.04 millimole, or millimolar. Subtract 0.404 millimolar, so then this is going to end up with 0.16 millimole. Just a DDA. Okay, not even equilibrium icebox, it's just actually quantifying how much was produced and then deciding how much of the two reactions produced. But I would definitely write down a BDA for that, because you may not consider how to account for each of those differences. Be okay? So 2, raise your hand. A, B, C, D. All right, so I have a fight between A and B. So tell me how you guys approach 2 here. We had binding oxygen to A and the binding of oxygen to B, our 1-step elementary processes, which is true regarding the constants for the rate forward binding to oxygen for compound A and B. So my people who said A, why do we say constants, the rate constants are equal? Let's get an explanation here. Were you one of them?
I just tried looking at the slope of the graphs, see
which slope? Like which A, B, AO, or BO? A and B. So if I look at rate of change, let's go to like 6 seconds maybe. So A went from 0.10 to about 0.05, right? What did B do? So maybe about 0.06. So is that, it looks very similar, but it's not exactly the same rate of consumption. So that's one way to look at it. And when I first did this, I selected A, but they're not exactly equal, but it does help closely look at the graph. B people, what do we look at? Say again? Right, the slope again. So we're looking at rate of consumption of A and B. So the rate of the forward direction. So A looks like it's going a little bit faster than B, meaning that it's being consumed at a faster rate, so rate forward's faster at that point for A versus B. Therefore, the K constant should be greater. That would be a close call because the graphs are not extremely different. So B should be the better answer. 3. So we're looking at equilibrium constants. So raise your hand. A, B, C, D. All right, you can participate in my survey, guys. I don't want to go over homework if you're not going to help me out here. A, B, C, D. Okay, so most of us said B, majority rules, it is B. How can we view that from the graph? I'll pull the graphs back up. So equilibrium constant for A is larger, or sorry, for compound A is larger. So you're looking at the concentrations at equilibrium. So tell me specifically what you're looking at here.
For the product or over reactants, so the first table you have 0.6 over 0.4, and then for the second table you have 0.46. So the equilibrium constant for A is
Great. So you're literally just looking at the concentrations of products versus reactants because that's what the K expression represents. But you could also just look at the graph and see that the AO product is higher at equilibrium than the A reactant, so you're going to have products favored, meaning K greater than 1. Over here on B, your B is higher than the BO product, so you have more reactants than products at equilibrium, so K is less than 1. You could do graphical analysis or plug in numbers and find the K values. So B is good. 4, what do we say? Which is true about the forward and reverse reaction for compound A? A, let's get a little hand raise. A, B, C, D. Right, so I got one group was correct. It was you did have to look at the time specifically, but if you look at 12 seconds, okay, D 12 seconds. Notice what's true at 12 seconds for both of these situations. What's true? So they all have zero slope, meaning we're at equilibrium. So the rate forward equals rate reverse at equilibrium. That's just a fact you should know. So that was the most, if you look at 12 seconds, it was the most obvious answer for that one. So that was 4. 5. So this binding of oxygen to A is exothermic. If the reaction occurs in an insulated container, which is the following most likely is going to result as the temperature occurs over time. So this is a temperature versus time graph, and it's just asking as the reaction is occurring, what's happening to the temperature of the insulated container. So raise your hand. A, B, C, D. Okay, most of us said A, majority rules. Why does it level out? This is, I'm sorry, let me back up. This is an exothermic reaction, so what's happening as the reaction occurs? Temperature is being, energy is being released, which should then increase the temperature of the system. And really, this room, so they're all consolidated together in this case because it's an insulated container. So the temperature is increasing, but why does it level off? Okay, or Taz, go for it. Because no, you're good.
At equilibrium, you don't really release more energy, so temperature won't change.
So the temperature begins to dwindle. Temperature change begins to dwindle because we approach equilibrium. Once we're at equilibrium, it's still releasing energy, but also the reverse reactions occurring, so we're consuming energy. So this constant release, consume, release, consume, release, consume. So there's no overall net change in temperature. So that A should be correct. Good. Now 6 was a little bit more elaborate. Okay, so at time, where did you guys indicate reaching equilibrium? What were you looking for? Zero slope, right? So we're looking for like, right here someplace to show the equilibrium is going to achieve because both forward and reverse reactions are equal. At time t, what's the relationship between Q and K? What do we say? Was K greater than, equal to, or less than K? Any takers? I got one person said less than. Raise your hand if you say equal to. Raise your hand if you say less than. Raise your hand if you say greater than. I have 4 people. You guys gonna help me out here. So JT, why did you say less than?
I said less than because the reaction is going into equilibrium in the forward direction.
How do you know it's going in the forward direction?
Because the A has a
Okay, so A is decreasing still, and AB is being produced still. So we have, what was the reaction to A to B? Yeah. So it was A plus 2B equilibrates to AB squared, or AB2. So at time t, you can see that the concentrations of product and reactant are equal, but that does not mean it's at equilibrium, nor does it mean that Q is equal to K, because Q equals K means that Q means it's at equilibrium. So because the forward reaction continues to occur, and you can see that by production of product and consumption of reactant, then you have to know that Q has not met K yet, so Q is less than K, and you would still justify it by looking graphically at how the concentrations continue to change. So that's the best way to phrase that. Any other questions on that one? Okay. At equilibrium, what's the relationship between the rate of decomposition of AB and the rate of consumption of B? Right, what'd you get, William? Yes, because who was double though, by the way? So look at it now. This actually has nothing to do with like the equilibrium aspect of it. So you could look at the rates of change, but what we have graphed here is A and AB, which they're a one-to-one relationship. So you should see that those are really kind of close in their consumption and production. So look at B. So B should be consumed how higher? Twice the rate. So B should be consumed at twice the rate that AB is, or decomposed is how the phrasing was. But yeah, so the reverse direction, that's being decomposed. The forward direction is being consumed. So B is consumed twice the rate that AB is decomposed in their reversible reaction. So D, you had given some given numbers for AB, and 1 liter container reaches equilibrium. If there are 3 moles of AB present in equilibrium, what's the value of K? How do we set this up, guys? Megan, help me out here.
I set up an ice table.
Okay, so we're setting up an ice. What do we know?
That it's 6 molar.
So A, and how do you know it's 6 molar?
Because it's a 1 liter.
So it's 6 moles per 1 liter, okay? And
I ended up putting, well, no, the new equation also said there's 9 molar for B.
okay,
And then you ended up with 3 molar of AB2. So you have to have 3 molar.
okay. So since we know the change, we don't have to really solve for x's. So I saw a couple people with x's on the paper. You don't truly have to solve for x. X has now been solved for because we know the change. Here was we added 3 molar.
And that function says there 1x, so you can add, or when you subtract 3 from
Because this is a one-to-one relationship, so we're subtracting the same 1x equivalents.
and subtract 6 from B.
Why 6 here?
Because that one is a 2x here too.
Okay, so we're essentially subtracting 2x, but we know that x equals 3, so then essentially that means we're subtracting 6. So then what's equilibrium conditions here?
It's actually 3 molar for everything.
3 molar for everything, but then how do you solve for K?
You put it in the expression, so you end up having 3 over 3 squared minus 3.
So 3 molar over 3 times 3 molar squared. Okay, so what can I cancel? The 3 and the 3, so then I get 1 over 9, which is like 0.111 repeat. Okay, so this K shows that, well, sorry, at this new temperature, this was the weird part, as you guys probably noticed, and I try to make sure we look back to reflect on the graphs. This graph at this temperature shows what's favored. Products or reactants? Products are favored because they're higher at equilibrium. So then we change the scenario and it says same reaction, different temperature, who's favored? Say again? Reactants, right? So sometimes if you have a graph, try to verify your answer is correct based on the graph, but then this one didn't help because it was a different temperature, so that's why we're okay with reactants being favored here. All right, so let's go ahead and switch modes. I need to show you guys my graphical analysis of loop facts, which is not really a graph like this. We're going to look at changes occurring over time. So graph this with me as we go. And then we're going to go to our lab, okay? So on part, maybe like animation 3 of your website, or of WebQuest, it had you looking at dinitrogen tetroxide, equilibrates to 2 nitrogen dioxides, and it didn't tell you the delta H, but it's like, I'm just going to put 100 kilojoules to show you it's what? Endo, okay. So you want to draw this graph with me someplace? Okay. So we have a reaction. We have an endothermic reaction. We're going to graph concentration changes over time. And I'm going to cause a couple of different shifts in equilibrium. So I'm making a really long graph to show that changes over time. So this is concentration. This is time. So normally on an equilibrium style graph, we always graph both reactants and products. So if we're graphing both of them, I'm going to just give us a starting point and just say that we have this many products. Oops, not a straight line. Okay, so one thing about Le Chat's is we always start off with a system at equilibrium. Okay, because it's at equilibrium, then we shift it. Like we cause the stress, we change temperature, we change the concentration, we change the pressure, we change the volume. So it wants to reestablish equilibrium over the changes that it can do. It can only really shift left and shift right though. So we have to start off at equilibrium. So how do I draw these first lines? Zero slope, right? So products in O2. Just remember that's in O2. And then I'm going to put reactants like down here someplace. And this is N2O4. All right, so they're at equilibrium. They're at equilibrium. I want you guys to think about what's going to happen if I add NO2. Immediately, what's going to change to my graph if I add NO2? There's a bump up, right? So there, NO2 is right here. It's going to actually jump up into like a straight vertical line. But then what does it do to equilibrium? It's going to shift which way? Left. We increase a product, it has to shift the opposite direction to do what to the product concentration? To end up, it needs to do what to this to achieve equilibrium again? Decreases. So I've increased this, there's a bump in the graph. Now this has to shift left. When it shifts left, this concentration is going to decrease, this concentration is going to increase. So this is going to decline, but not all the way back down to its original concentration because there's now more of it in the system. So it's going to decline. Okay, but what's going to happen to this? It's going to increase at kind of like a hill. It's not going to be a peak. Okay, like that. All right, so now after this shift, I'm actually going to annotate what's happening down here. I added NO2, which was a product, and you guys said as the products are added, we shift left. Okay, so it's at time 1. And then we reestablish equilibrium. That time is a little bit off. It's actually over here. Okay. All right, so now I want you guys to, at time, whatever this is, time 2, I want you to add N2O4. Okay, so we're at equilibrium. What's going to happen? I need you guys to help me out here, Taz. On which one? N2O is going to bump. N2O4 is going to bump high. Okay. So N2O4 is a reactant. I've increased reactant. Which way does it shift everybody? To the products, right? So we need to make products. So what am I doing to this line up here? A steady increase, okay? It's not a peak. So as this steadily increases, what's happening to reactant N2O4? It's going to steadily decrease, but it's not going to come down to the original because I still have more of it in the system. Okay? So now I'm back at equilibrium. So this one was a shift right. Now at time 3, I'm going to decrease the volume of the container. All right, so think about it. Which way will it shift if I decrease the volume of the container? Why am I shifting left? Okay, so essentially what has decreased volume done to the system? It has, inadvertently increased the pressure. Your job is to find a way to decrease that pressure, which means go to less moles. Okay, so we need less moles, and that's a shift left. Okay, so is there going to be a sharp increase on either of these? No, because I didn't inject a certain amount of product reactant. So these like peaks are only for injections of a certain concentration or a certain reactant product. This is going to just be a steady change. So how does N2O2 change? I'm sorry, N2O4 change? Increase or decrease? Increase. So it's going to just be a kind of an increase like this. Now I'm choosing how much because I'm just making up how much I've added, so don't pay too much attention there. All right, so this is going to increase, and what's going to happen to product? It's going to decrease. Now I don't have enough room for that, so hold on. Because this one actually decreases at twice the rate, so I'm trying to mimic that sum a little bit just because it's a 1-to ratio. These aren't beautiful, guys, but you guys are seeing the points here. All right, so we've decreased the volume. It increased the pressure. We decreased the pressure by shifting to less moles. I've made more N2O4, made less N2O2. Now let's increase the temperature. All right, so think about it. Which way will this shift? Right. Why will it shift right? Right. So this is a very, very peculiar phrase that we did learn Friday. It has to be increasing temperature though. So if I increase the temperature, it favors the endothermic direction. But why is that? Because what does the reaction need to do with all that extra energy? It needs to consume it, right? So it needs to consume it. So it's going to consume it by using it up as an endothermic reactant, as we could say, but we don't ever want to call temperature reactant because it's not. So increasing temperature will favor the endo direction, which is going to, for us to be a shift right. So what happens to N2O2? It's going to what? I'm sorry, NO2. What happens to NO2? Increase. Let's say I increase the temperature a whole lot. This one, yeah, it's going to be a steady. Okay, so I'm just going to go kind of high. And what happens to N2O4? Decrease. And I kind of did it at different rates, as you can see from the concentration ratios. Okay, so a couple of the points that I made over here with concentration changes was that if we increased or decreased, or sorry, if we decreased the concentration after it had been added to, we don't go back to the original point or below. We only stay above. So I tried to strategically show you guys that here. We're kind of above the initial, and over here, when it declined again, and we're still above the initial. So make sure you're clear on that because you will see graphical analysis like this. Like, how would this change? How would this graph change if I added the X? How would this graph change if I added Y and like pick the correct graph? Okay? Those are like on multiple choice. All right, let's do our lab. Oh, I'll go back to check that textbook. Okay, so this is an easy lab, guys. So we have about an hour. Everybody has their lab notebook now because either you had it or I gave it back to you today. I would go ahead and knock this out in your lab notebook so you're not trying to rewrite. Right? Don't waste your time. It doesn't have to be beautiful, Fatima and Darcy. Just it's there. Okay. So I'm going to show you guys where these things are in the back. But you will be working in 2s or 3s just so everybody has some hands-on with respect to this lab. So meet me in the back first, and then I'll tell you where we're going from here. Just a little bit. Grab whatever off my desk here. Lots of stuff. So you guys have like a picture back here. Get your lab station right there. You can play it off. Grab a striker. I'm going to remind you of some keys. Grab a striker. Alright, so in almost the lab station, I know that I only put one bucket at each lab station since you guys can share, but you guys can have up to 4 to 6 people, I suppose, per lab station, right? But you have groups of 3 mostly. Alright, so let's read 3, 2 to 2. Okay, cool. So here we have cobalt 2 chloride in this pH solution. At the very beginning, I'll tell you how much you're supposed to get. We're supposed to get 5 milliliters, right? You're going to do that. I'm going to put the raspberry pipe back first. Now, I'm going to put 1 that we feed both of these containers, just so we're not like contaminating a bunch of stuff. This cobalt cannot be down the drain. Cannot be cobalt down the drain. On the waste container here to the end of the lab, so you guys can never feed from there. And then boiling chips are something that you'll put into a test tube. So in our test tube, we'll put like 3 or 4. They're called human stones, or like like we rub your calluses off with. But these just help control a boil, so it's not spurting and like when splashing out of the test tube. You'll need a couple of those. At the end, you will filter these out and not pour these down the sink, or do not put them in there either. Calcium chloride, a big container of it. Essentially grab like 3 clumps or 2 clumps. Clumps are in here. You're going to use just a scoopula to get it out. I have 2 scoopullas in the back. Some people are not putting them back in the lab because I don't know the place. So just make sure you're left in the scoopula like this. Okay. Silver nitrate should be in your If it's not, I have the 2 molar here. I put 1 molar here so I can mark it. I'm sorry, 0.1 molar. If 0.1 molar does not work for you, I have the 0.2 molar here, which is a little bit more concentrated, might work a little bit better. Most of us have saturated sodium chloride. I just resaturated some, so this clear solution is saturated sodium chloride with water with salt in it. So if you don't have enough of that at your station, some groups are lacking some things, you will have to share across lab stations, so you have to ask first. The copper 2 sulfate pentahydrate is here. I only have 1 of these, so it's going to stay here. And then most of us have acetone in our buckets. Acetone is going to be the 100% acetone, like you can like here in a car shop with. That will destroy my plastic graduate pipette. So I put some little plastic squeezy ones in there. I don't care if those get destroyed. Acetone destroys plastic. So in general, like some plastic. So I don't want you to use my graduate ones in here. Bunsen burner, I have not turned the gas on yet, but the Bunsen burner, if you don't know how to set it up, you can turn it in my lab and go for honors. Kind of how to do that. It's like 4th or 5th page back. And I gotta turn the gas on. The last thing is the concentrated 12 molar HCl. I'm gonna put that in the deep in just a second for us. Otherwise, you guys can do next. Drop on. Just clean room in your lab notebook so you're not, rewriting. Yeah, JT, I cannot move. Put it in here, I can't stay here. Yes, do not remove the ring. Bring your stick, bring your something back in here. I have plenty of plastic little pipettes in your container if that's what you need to transfer a milliliter. If you don't know how to read these, if you have graduations on them, that might help just like for a quick 1 mil transfer between your stock and your test tubes. If you have 4 or 5 milligrams, not every gets to do something.
This one. It's really dirty.
Are you good? You done with the cobalt?
That's
We are the University of Sweden. This doesn't go yellow with yellow.
Alright, we need to go ahead and start the next step. Like now, okay? If you've not set up your Bunsen burner correct and you have to we'll take the Bunsen burner away from you. You guys can share a Bunsen yeah, watch it out.
Go ahead and get 3 minutes. That's 3 no's.
Oh, hold on, guys. The gas isn't on yet. Hold on. I went and got the acid, but I did not turn the gas on. Sorry. And the gas will be on in about 3 seconds.
I hear somebody's gas turn off. Oh, it's mine. Look, somebody just turned it off. Here, come back. Come back.
Good job.
It's supposed to be 7 years.
All right, those of you going to restart the heat trials, raise your hand. Heat trials, that should be basically everybody. When you hit the Bunsen burner and it's turned on, listen, look up here if you need a picture. Once the Bunsen burner is turned on, you have an inner blue cone, right? The inner blue cone is the hottest part. Do not put the test tube directly into the inner blue cone. You need to hold it way up. The heat will radiate up and do its job. Okay, so do not put the test tube into the flame. But we need to start that now. Like, let's go. Alright, so then what do about
Alright, some of us should be getting a cool bath ready, which is a ice bath. You don't need very much ice, but you see a small beaker, a couple pieces of ice. That will be what you're doing after the heating shower. Alright, somebody can be working on the next trial, pass the hot and cold trials. Okay, you have enough people to do that? Once you feel satisfied with that color change, you can move on.
That might be what we use, right? White lumps. And then I'll put it in lumps are rigid, white, solid. Rigid, white, solid. And then use very thick. That's a good sign for it to be there. Rigid, white, solid. All right.
Alright, we should be to this calcium chloride step or past it. Let's get to calcium chloride.
So what are you going to do? Yeah, I already measured So you want to write this one? They dissolve like blue and came off like a white. Gave off like white powder. It's like the dark like
Some of you guys are deciding to move on. If you want to get HCl, I'm available. I'm going to stand in the back to get you HCl. So bring me a test tube when you are ready.
What is it? What was that? Static form. It's like words one of the layers. This is the third one. When the HCl was added, the color immediately changed to dark blue. I think it's this. And then after a given time, I don't know how you want to do it. After a given time, yes. After a given time, it's blue layer on the bottom.
Guys, listen. Before you begin disposing of things into places that are not labeled and you don't know what it is, I've got people now contaminating my solution by putting their boiling skins and their copper or their cobalt fluoride in my sodium saturated fluoride solution. This is not a waste. The one that's labeled waste is where you're putting cobalt. What are you doing with the rest of the things that you need to filter? Do you have a filter paper in your bucket? You can set up your own filter. Do not dispose of things if you're not sure where to put it. Ask me first. Thank you. Read it really, really, really slow, he said. You guys look at the area where it's actually, it looks good. You still find the results. Like 5 minutes left. 5 minutes. Last call for HTML. I'm going to get out for the next 5 minutes.
It's a little darker. Double check.
Do not take the single ingredients to your station if you can find them.
Introducing pebbles do not cause
Alright guys, we leave in like 2 minutes, so if you don't clean this up now, you can clean up during intermission. If you're doing stuff during intermission, you have like 2 minutes to figure out what you're doing right now.
pushed it down.
Take a picture of your results. Make sure it's not there when you get back. Take a picture of your results. So that result is correct. Alright, the bell's gonna ring in about 30 seconds, so I'll go ahead and call it a day on cleaning when we get back. Are you guys logged off laptops? I can help with these up. Are you logged off? You guys just log them off. I'll put your laptops up.
So you do anything with the
Alright, we'll just be the figure out.
Don't forget your goggles.
William, are you good?
Okay, yeah.
So now's already leave. Because you can't even or leave it there to be back. She'll be back, right? Bye.
Bye. Lungs are clean. Cleanish.